So good day, everybody. Sorry, I had to skip one class today because of some meeting. Could anyone remember what was the last topic we discussed at our last class? Did we have Did we discuss the frequency dependent circuits? Hello? Did anybody hear me? Hello?
I don't think we did, sir.
So probably you could remember what was the last topic we discussed. Because as I said, because of two group, I had a little bit mixed of what we have. What was the last? Have we started discussion on the operational amplifier at all?
Last we discussed about non-inverting amplifiers.
So we actually stopped with the non-inverting.
Yeah.
Okay, excellent. So let's go further and discuss some other type of amplifier. We have now only 1 hour. Okay. First of all, you will have some assignment in order to review the topic on amplifier using the annexed one of the laboratory work description. I think so now I have to wait a minute. I will share my screen now. So here actually what we started to discuss, and we came to the inverting amplifier circuit. So this probably was the last we had discussed. Did we spoke about summating amplifier too?
Yes.
Okay. So probably it was the last what we had discussed, this idea of summating amplifier. And what about the follower? Probably no. Okay, so let's just go back to the inverting amplifier and then we come to the follower. So I just wanted to remember what we have discussed, that the idea of inverting amplifier. So we have a device which we apply the input voltage, some input voltage to the input resistor R1, and the voltage causes the current to flow through the input resistor and the feedback resistor, because there is no current going inside, and flowing through the output through the feedback resistor, the current, which is the same as the input current, causes the voltage drop between the input, the amplifier inverting input and the output. To match the direction of the flow, we understood we have to admit that the output voltage is negative, so it's below it's lower than the voltage on the inverting output. The connection of the non-inverting input to the ground of the circuit, to the point what we actually assigned, which voltage is assigned to 0, or which potential is assigned to 0 by definition. So we got here on the other input of the amplifier, so-called virtual ground condition, because we know that when the amplifier has a feedback, if there is a feedback circuit, so then it works in such a manner that the voltages on the inputs are equal. So this was a inverting amplifier. So calculating together or adding, putting together the expression for the current through the resistor chain and the Ohm law for the feedback resistor relating the output voltage to the known current that flows through resistor RF, we got the gain of the amplifier as the ratio between feedback resistor resistance and input resistor resistance. Another example, so we discussed how we could modify the inverting amplifier to get a summating amplifier, and we discussed a little bit what is the reason to use a summating amplifier. It's one of the example why do we do this. And now let's consider another example of the amplifier. So the amplifier which is called the follower. So if we look at this amp, so we see certainly the feedback, and following that we have a feedback, what we could say about the voltages on the positive and negative terminal, or positive negative inputs. So there is a feedback. So how the amplifier should behave? What could we say about voltage UE applied to the positive, to the non-inverting input, and about voltage applied to the negative input?
Should be equal.
They should be equal, exactly. They should be equal, and then it means that for this circuit, the output and input voltages is just equal. The gain of such a device is 1. That's why it's named follower. So actually, the output voltage just follows the input voltage. And the question, why do we need such kind of device, such kind of amplifier, is that it's in fact a current amplifier. So it doesn't amplify voltage; it's amplify current. So because it has an extremely high input resistance, nearly infinite. It's not an infinite in fact, but it is really very high. It's over giga ohms, and that's why the follower doesn't take a current from the voltage source. But as an amplifier may provide more or less high current from the power supply, this follower could keep the voltage high even when a load, I mean the resistance, it is or load, the resistance, effective resistance switched between the output and ground may be low enough. So for the real amplifier, so the real amplifier has actually internal output resistance about 40 ohms. And for the input, for the next stage up to 40 ohms, or even in the order of ohms, it's fine. It still could keep quite high voltage. We may modify a little bit the follower circuit to add here some amplification. And if we connect a resistor in a feedback circuit and add the resistor connecting inverting amplifier with a ground, in this case, we have a so-called non-inverting amplifier. The mass of the amplifier is the following. So we could describe the current that flows through the output to the ground via the chain of resistors RF, Ri. This one. So we may calculate it dividing with output voltage, to the total resistance of all chains. So U out divided by R input and R feedback. So this is a current that we have floating through from the output to the ground. Then, knowing the current, we may calculate what will be the voltage on the resistor R input of this resistor. And this will be this current times resistance Ri. But we should note that because we have a feedback, the first rule of the amplifier requires that this voltage and this voltage should be equal. So in fact, the voltage over the resistor Ri is an input voltage. Adding all these together, so actually expressing, for instance, I as a Ui divided by Ri, we put it here, this equation, and calculating out the output voltage, we will get the relationship between the output voltage and input voltage. So we could find that gain, in this case, the gain is input resistance plus feedback resistance divided by input resistance. So this gain always is greater than 1. So we see that if we shorten here Ri and Ri, we got 1 plus R feedback divided by Ri. This means that the gain always is greater than 1. The non-inverting amplifier has a it has some good features, that it has very high input impedance. And another circuit what should be analyzed actually thoroughly is so-called a differential amplifier. It's a very important circuit because actually it could be used with some different kind of sources, of signal sources that are not grounded. So if we have no ground in the signal source, but just some 2 points, and have to measure the voltage between these 2 points in respective to the ground, so we may use a differential amplifier when the signal source is connected to the inputs of the differential amplifier. The output of the differential amplifier is a gain times difference between the voltages on the inputs. So let's try, we may try actually to describe how this amplifier works using, I marked the input voltages and on pupils as U3 and U4 because we need this notation in the next consideration. So, and for the differential amplifier, let's look actually what do we have. So we may calculate the voltage U5, the voltage on the non-inverting input, as using this divider built on the resistors R3 and R4. And it's obviously will be U4, so the input, this input voltage U4 divided by the sum of the resistance R3 and R4. This gives us a current flowing in this through these two resistors, and then we multiply it once more by R4 to get the corresponding voltage drop over R4. So it's actually the usual voltage divider equation when the total voltage over divider is U4 and we are looking the voltage on the second, on the bottom resistor R4. So this is a voltage U5. From the top circuit, we understand that we have here some current flowing either from U3 to U0 to U out, or from U out to U3, never mind in which direction it's flowing. But most important is that the current through resistors R3 and R4 will be the same too. I make here notation R3 and R4 on pupils. So usually in differential amplifier we try to match resistors R3 and R4. In fact, it's not necessary to match the resistors itself. We have to match the ratio between R3 and R4. They should be equal in the bottom circuit and in the top circuit here. So if they are equal, the amplifier works well. I wouldn't spend the time to demonstrating it, but just take it as a known, yeah. And you may try to prove it. Just try to repeat our calculation, replacing the R3 and R4 here with some other resistor in some other notation like R3 prime, R4 prime, and look at what will be the output voltage, how the output voltage will be related to the voltages U3 and U4, and you easily could find that the relationship between output voltage and the differences in input voltages will be like that. If we assume the ratio between R3 and R4 equal for both our upper line and upper circuit and bottom circuit. Well, but up to upper circuit. So we actually could equalize the current flowing through R3 and current flowing through R4. Let's just express the current flowing through R3 as a difference between voltage in the one from one side and another side of the resistor. So actually the voltage drop on the resistor R3 will be the voltage U3 minus the voltage U5. We have here the voltage U5 just because of the first rule of the amplifier. The voltages here are equal. So this is the one expression for the flow, for the current. From the other hand, it will be current that flows through the R4, and we may write it down for following Ohm law as a voltage drop over R4, which is a difference of U5 minus U out, divided by R4. So by combination of all these two equations, this one and this one, we actually has to exclude U5 out of this equation, making some algebraic transformation, we will get finally the result. Please try to make this transformation by your own and make sure that indeed the output of the differential amplifier is a proportion to the difference in all the inputs. In this circuit, the U4, the voltage, the input, this bottom input, when the U4 is applied, is actually non-inverting input, and U3 in the this upper input where U3 is applied is an inverting input, because the corresponding voltage comes with a minus to the output. The gain of the differential amplifier is just R4 divided by R3. As you see, it's very similar to the non-inverting, to the inverting amplifier, so the difference between the feedback and the input resistors. The differential amplifier, except of just so this gain R4 divided by R3, the gain is a gain for the differential signal. So it's described how the difference between the input voltages will be amplified. Except of the differential gain, the differential amplifier has so-called common mode gain. The common mode gain is measured when the both inputs for the differential amplifier are connected together and some arbitrary input voltage is applied to the both input 3 and 4, so to the both inputs. So we connect them together and apply some voltage, and then we see what will be on the output. Would you say, or would you expect, what should be the theoretical value of the output voltage for the common mode signal? So what we are expecting in theory for the ideal differential amplifier, if U3 and U4 are equal, what should be the output? No? Any ideas? So if U4 and U3 are equal, what this equation should say? What this equation will say? What will be the output if U4 and U3 are equal? 0, yes. So for the ideal differential amplifier, when you have the theoretical common mode gain, so the common mode gain will be 0, because if we have the same voltages on both inputs, we should have 0 for the ideal amplifier. For the real amplifier, because of little differences in the ratio R3 to 4, because of the differences on the operation on inverting, non-inverting input of the amplifier, because of non-idealities, what we could meet in real life, the output voltage will not be the absolute 0. It will be some very small voltage, and the corresponding relationship ratio between the output voltage in a common mode and the input voltage in common mode is named as a common mode gain. So this is a common mode gain. So when we connect together the inputs of the differential amplifier, apply some voltage and see what is on the output. The ratio between output and input will be the common mode gain. The differential gain is just the usual gain what we are calculating beforehand. Yes, so and this is a ratio actually between the output voltage and the difference between input voltages. And of course, we could understand that the differential gain is generally higher and much more higher than the common mode gain. And then we define for the differential amplifier, so call it common mode rejection ratio, or CMRR. The common mode rejection ratio is defined as a ratio between the differential gain and the common mode gain. So the value of this ratio should be very high. So for the typical differential amplifiers, it easily could be from 100 for the very poor amplifiers to up to 10,000 for the quite more or less good amplifiers. Sometimes and often the common mode rejection ratio may be expressed not just as a ratio but in decibels. So for instance, the common mode rejection ratio corresponding to the ratio of 100, if we try to calculate it in decibels, we will get, so the logarithms of 100 is 2, times 20, so we will get 40 decibel. And here we have 4 times 20, it's 80 decibels. So often the common mode rejection ratio is expressed in decibels. How could we increase the common mode rejection ratio of such kind of differential amp? And generally, let's consider this differential amp. For this amp, we have a certain one of the drawbacks. It's a low input resistance. So such kind of differential amplifier has, frankly speaking, quite a low input resistance, especially for the channel U4, for this one, for the input. It's absolutely easy to understand, so that then the input resistance will be just R3 plus R4. For this input, it's not so easy because we have here some influence from the output, but generally we certainly know that the voltage here will be this U5. We may evaluate what will be the input resistance. It's actually more or less similar to R3. So this limit application of such kind of differential amp, especially for the measurement of biological signal, when we have to have a very high input resistance. So how could we increase the input resistance of this differential amp? What we may use, which circuit we may add to the input to increase the input resistance? We already discussed it. So we need some buffers to disconnect our sources, which require high resistor from disconnect our sources from the direct connection to inputs of this differential amp. So what should we add? Which circuit we should add here before our signal will be connected to our signal source will be connected to the inputs? So we need to add something here.
A follower.
Followers, exactly. We may add followers here. So if we add followers, we actually had an infinite resistance both for one for the both inputs. So the both for inverting and for non-inverting. If we already added these followers, we actually may get something more from the followers adding not the followers but inverting amplifiers. So for this non-inverting amplifiers, for this we already increase a little bit voltage U1 or U2. So, and the voltages which will be passed to the input 3 or 4 or the differential amplifier will be actually increased, will be higher. This circuit may be used, but it has one additional drawback, that the first stage, actually doesn't work as a differential stage. It's not a differential stage. It has to take U1 and amplify it as high as possible, or take U2 and amplify it too. But sometimes, if we are actually interested, we are interested in the difference between U2 and U1. Otherwise, we wouldn't use a differential amplifier. So the voltages U1 and U2 itself may have some kind of high common mode. And this common mode will be amplified too here, and sometimes we couldn't amplify neither U1 nor U2 quite high because they goes to saturation because of very high common mode. So we would be interested if the first stage works as a differential stage too, so would react only all the difference between U2 and U1. And we may do this by just joining together this resistor R1 and R1 here into one single resistor, or actually dropping here a connection. We will not connect this R1 to the ground, but we will connect them. Together, disconnecting from the ground. So if I redraw the circuit, I will get such circuitry. So, and please mark somewhere, or that this circuitry is actually our the most probably important circuitry in all our course, because we name the circuit as an instrumental amplifier. So it's actually the heart of every biological signal or biopotential measurement device or any biological signal measurement device or any measurement device generally. So because an instrumental amplifier allow us to measure indeed the voltage difference between two arbitrary points independent whether the points are connected to the ground or the source is connected to the ground or not connected to the ground. And for human biopotential measurement, it's just exactly what we are looking for. So we are going to measure the potential difference of voltage across different points over the body surface. So this is an instrumental amplifier. So it has a two-stage. Let's see how the first stage works. So the second, we know how it works. The second stage, the output voltage will be the gain of the second stage, R4 divided by R3, multiplied by the difference in voltages U4 minus U3. But how this voltage U4 minus U3 is formed by the first stage? Actually, this voltage U4 minus U3, it's a voltage drop over all this chain R2, R2, R1, and R2. So U4 minus U3. So the difference of voltage between these 2 points is actually the voltage drop over this all long chain. And how could we calculate this voltage? Let's see how we get it. So if we have the U1 and U2 absolutely equal, because of this feedback, so we have a feedback for the first amplifier and we have a feedback for the second amplifier. Because of the feedback, the voltages here on the inverting inputs of both amplifiers will be correspondingly equal to the input on the non-inverting inputs, to the voltages on the non-inverting inputs. So actually the voltage here will be equal to U2 and voltage here will be equal to U1. When they are both are equal, U2 is equal to U1. So then the voltage drop over R1 is 0 and there is no current flow through R0. That means that if no current flow through R0, the only one way how to current could flow, it could flow only through the whole chain R2, R1, R2. Because following the second rule of the operation amplifier, no current flowing here. So if we have equal voltages on the input, we have 0 voltage drop over R1, so the current over the R1 through the R1 is 0, and the same 0 current flow through is through R2 here and here. So there is no current through all this chain, and this means that voltage here and here are equal to U4 and U3 are equal. So we have to have 0 on the output. If they are different, so let's imagine that U2 is higher than U1. So if they are different, so U2 is higher than U1, so we have a flow of current. So U2 is higher, U1 is lower, so we have a current flowing upward. And this current, which is actually equal to U1. Okay, I took U1 is higher. Okay, let's see, U1 will be higher, so current will flow that way. Yes, U1. Yes, let it be U1 minus U2. So U1 is higher than U2, so the current flows downward. And this current will be equal to U1 minus U2 divided by R1. So it's a current through resistor R1. The same current has to flow through the both resistor R2. And then the total voltage between this point and that point is the current that flows through all the chain times the resistance of all the chain. So the current U3 minus U4, voltage U3 minus U4, is equal to the current U2 minus U1 divided by R1 and times R2 plus R1 plus R2. So the result, it's not written here, but the results actually will be, I have to write it down. So then we put this U3 minus U4 and add it together to the U3 minus U4 minus U3, express U4 minus U3 for the differential amplifier. And finally, I will get for this amp, I will get the final equation. I have to write it down now. So if I combine all together, my equation will look like U out is equal to, so the first stage gain R1 plus 2 R2 divided by R1 is the first stage gain. Then the differential amplifier gain R4 divided by R3 and times U2 minus U1. So this is a differential amplifier too, because it reacts on the difference. The bottom, which comes finally to the non-inverting input of the differential amplifier, it's non-inverting input. The upper input is inverting input, and so the output is proportional to the difference between these two inputs, U2 minus U1. So the gain depends on both the resistors R2 and R1 selection and R4 and R3 selection. Very often and what is important for the amplifier to work correctly, actually it's even not, it's even not so important whether the R2 and this R2, how equal they are, because we see that we don't use anywhere here in the calculation the equality of the R2 of these both resistors. So they may be a little bit different. In any case, the voltage what is generated here will be just R1 plus R2 and R plus all these three resistors added together. So it's not necessary to make this R2 ideally equal. But what we should do, we should to make either ideally equal the ratio between R3 and R4 and R3 here and here. To do this, sometimes the resistance R4 is made adjustable. So we may adjust the resistance of R4 to tune this differential amplifier. So how the tuning is done? So we connect together the both inputs, U2 and U1. We connect them together. We add some voltage here, and then we try to adjust the value of R4 to get the output voltage as close to zero as possible. So it should be actually very close to zero, and it means that if it's close to zero, it means that this amplifier doesn't amplify the common mode. This differential first stage increase a little bit common mode rejection ratio. When we're speaking about the calculation of the amplifiers, unfortunately, so we very easily may calculate the differential gain for the instrumental amplifier. But it's very difficult to calculate the common mode gain because we have to take into account all the non-idealities of the amplifiers, which actually very often are not known. So we know what may be the spread of the bias currents or the bias offset or offset voltages, so those non-idealities of the amplifiers, so the parameters is characterized non-idealities, but we don't know them for the particular amplifier. So that's why it's very difficult to calculate the common mode rejection ratio or common mode gain, and usually the manufacturer just assemble such type of instrumental amplifier and measure typical common mode rejection ratio, what could be reached with a optimal design, with the most probably some typical design of the amplifier. So the circuit what is used here, this instrumental amplifier require we have to have 3 separate op-amps, and we may connect them by our own, but we may rely on the manufacturers because the instrumental amplifier as a finite single chip are widely available on the market. You should note that generally the instrumental amplifiers are more expensive than a usual operational amplifier. It's easy to understand because one instrumental includes at least 3 E3 usual operational amplifiers. There is another type of instrumental amplifiers which employ another circuitry that employ two operational amplifier. I, frankly speaking, don't like this circuit. To my mind, it looks like not so well balanced and not so rigid, not so robust as this circuit. I prefer this type of the circuit. An example of the chip, one single chip instrumental amplifier is so-called AD620. One of the examples. Please don't consider as advertisement. Yeah? But this is one of the good example made by analog device. It's not only single one amplifier in the market. The same manufacturer produced AD623, which is superior comparing with AD620, has higher gain. So if you look at this amplifier, so we have the general inputs of this amplifier are, so here we have a power supply, plus supply voltage minus supply voltage. The amplifier typically works as a differential it works with a bipolar power supply, so we need to apply 0, minus and plus, but this particularly may works with a single power supply too, so from 0 to plus 5 volts. So it's actually may operates well already when the difference between power supply plus and minus is as low as 4.6 volts. So with 5 volts it works perfectly. So it means that it may be very well connected together, for example, with Arduino, using the Arduino output 5 voltage, the power source for the to feed the amplifier. So we have the input inverting and non-inverting inputs. So for V1 and V2, we have an output was absolutely clear, and we have the two outputs when we have attached a resistor to these outputs between RG and RG here, first and 8 leg of the package, and these RG control the gain of the amplifier. So for the AD620, the relationship between the resistor RG and the gain expressed like that. So here is a relationship between gain and RG, and here is a relationship between RG and gain. So if we set certain gain, what we are going to achieve, so we actually may use this equation to calculate what type of RG we need. The gain range from 1 up to 10,000. So it depends on the value. So if we don't connect anything to RG, if RG is infinite, the gain will be just 1. So for this AD623, the difference will be that this value will be not 49.4 kilo ohms, but it will be 100 kilo ohms. This is a quite low power amplifier in this extent that it doesn't require a high supply current. So his supply current, it's about 1.3 milliamps. It's quite stable, so the offset drift it's not higher than 0.6 microvolts per Celsius degree. So if it's heated, the output may get some additional DC component or shift, which is not higher than 0.6 microvolts per Celsius degree, and generally the output, the offset voltage is not higher than 50 microvolts. So it means that the difference between the inputs that cause output will be equal to 0 is not higher than 50 microvolts. It actually may work in the microvolt range. The input current is not so high, it's just 1 nanoamp, but generally for the other type of amplifiers is not so small too. So for very good instrumental or for very high class op-amps, the input current may be as low as several picofarads, some 10 picoamperes. The common mode rejection ratio is at minimum of 100 decibel. It means that it's higher than, so That's 100,000, the ratio between common mode or differential gain and common mode gain. And the bandwidth is quite high, it's about 120 kilohertz. That means that this amplifier may be perfectly used with all the biological signal. We very seldom need more than 20-40 kilohertz for bandwidth for the biological signal. Yes, it could be used with the ultrasonic for the ultrasonic devices, or in a high radio frequency range where the bandwidth goes up to megahertz. But for the biological signal measurement, it's very very good solution for the biological signal measurement. So speaking about the data about this amplifier, so I just remember that for every engineer we have to remember the mysterious word datasheet. What means that datasheet is it's a document what is usually published and accessible free of charge over the internet by the manufacturer, and the manufacturer uses datasheet to describe all the feature of his product, and the datasheet doesn't only contain the all the details of the parameter of the amplifier, but very often it contains also the typical circuits. So how should you switch the device, how you should connect them to work with it. So the datasheet is a main source of information about any electronic device, especially about microchips, about micro assemblies, about integrated circuits. It may be in a lower extent, the datasheet is important for single semiconductors like diodes or transistors, but still these elements has their own datasheets too, where some certain important information for the design, for the circuit designer could be found. So please remember that the datasheet is it's your friend and it's your helper, it's your source of information. Well, okay, so we actually considered now some examples of the very typical amplifier, and please review it by your own one more. I'll try to find where is it. Oh, yeah. No. Wait a minute. Yeah, so please find in your course, when we have this part by basic operation amplifier electronics, so you have here the laboratory assignment 2. You don't need, of course, do anything with this, but there is an Annex 1. So please review this Annex 1 in the manual to this lab 2. As to second homework assignment, I'm afraid that we will not have enough time to go through the calculation, so we probably do this next class, yeah? Because I'm going to show you how to calculate second order filters too. Well, so let's continue with our topic. So some examples of the functional amplifier. Generally, the history of the functional amplifier is related to the history of the analog calculation. I don't remember whether we discussed or not, but the concept of operational amplifier and its name comes from the word operation, what means a mathematical operation. And the operational amplifier was the main component of the analog calculation, of the analog computers. Generally, it was machines that simulate some physical process and was used to solve differential equations that actually describe this process. And up to now, this analog calculation is used, but now we name it not as an analog calculation, but as automatic or control algorithms or control circuitry. So we still proceed some data in analog form because it's faster. Sometimes it's faster than a digital form. So some functional amplifiers. So what from the name of what does the functional amplifier mean? So they they actually are used to represent some mathematical function. And generally, it's quite a number of functions we really could represent. And some typical example of what we actually described today, or we discussed today, it's a function of absolute value, or model, absolute value function. We discuss logarithmic function and anti-logarithmic function, and such several operations like multiplication, such as integration and differentiation. So how we could make such an operation, signal operation, using analog circuitry. As to adding and subtraction, we already discussed the summating amplifier. So this is an instrument. This is actually the functional amplifier too. It's provide us operation, some mathematical operation of adding, of subtracting. We know we know how to arrange an operations of multiplication by some constant. So we use just amplifier. We know how to make multiplication by negative value. So we use an inverting amplifier. So all the circuits was used in those prehistoric, let's say, prehistoric analog machines. Well, let's discuss as a first example the absolute value function. So the absolute value function is realized, or is actually implemented by different kind of rectifier circuits. We couldn't use just a pure diode, just a single diode and a resistor for the implementation of the absolute value function. What do you think? Why do you think why? So we always have to include the diode in some operation amplifier circuitry. We couldn't use just direct diode and a load and a resistor. Why do you think we couldn't use diode to make an accurate absolute value function? Is there any ideas? So may I use just a diode and the resistor? Or bridge circuit, okay, with a diode and resistor to get, if I have here some sinusoidal voltage, would I have here the accurate positive semi-waves of this input signal? Or they will be distorted somehow. Is there any comment, please? Hello? Is there anybody in here? Okay, so any comment? Yes, exactly, it will be lower. So if we have the input semi-wave like this, so the output semi-wave will be like that. Why? Yes, because diode eats 0.7 volts. It requires a forward bias, and it's actually subtracts this forward bias from the output signal, from the input signal, to pass it to the output. So that's why we never could get a fine rectifier, accurate rectifier, which indeed provide us the absolute value of the input signal. And we need to include it. We need to include the diode into some operational amplifier circuit. For this example, let's see how this simple rectifier works. Let's consider, I'll take a color and take another color here. Yeah, red one. Okay, so let's consider first what happens if we have here a positive voltage? So the positive voltage causes the current to flow through this resistor R. They are both Ri, so I'm arguing R1 and R2. So the input and the feedback, input resistor, feedback resistor. So it flows here. It could flow inside, so it should continue here. It couldn't flow through the diode because it is the opposite direction for the diode, the current, and it's flow here. So actually, when we have a positive voltage here, our voltage will flow, our current will flow through the chain of the resistor R1, R2, and RL, which actually load resistor. And then I get the current I is just equal to I divided by R1 plus R2 plus RL, and corresponding output voltage U out will be this current times RL. So I get RL divided R1 plus R2 RL U1. If you look at the values of the resistors, you may find that these values are selected in a manner that RL divided by R1 plus R2 and RL will be equal to 1 second, to a half of U in. Yeah? So if we have a positive voltage, so then when we flow through, we get here a half of input voltage. Okay, fine. Let's see what happens if we have a negative voltage. So if we have a negative voltage, the current will go in the opposite direction. The currents will have to go into opposite direction here. And now we see that if the current goes in that direction, then the current may flow now through the diode too. So if we have minus here, it means that we have minus here, and following the inversion, because it's inverting input, we have plus here. So for the diode now will be forward biased, and some current flows through the diode. So that means that our amplifier will be in a feedback. We have a feedback now. In the first, in the positive connection, the diode will be closed, and we could consider there is no connection at all, so the amplifier output even have not been connected to U out. Now it's connected through the diode, and we may neglect a little bit the diode. We will neglect the diode, consider that there is no diode at all, and we have a connection. We have a feedback. So if we have a feedback, our circuit, our amplifier immediately form an inverting amplifier. And for this inverting amplifier, U out will be minus R2 divided by R1, U in. As we see, R2 and R1 is selected to have a gain of 1/2. It will be the same 1/2 from U in, but with a minus. So what do we see? So we see that U out is equal to 1/2 of U in if U in is positive, and 1/2 minus 1/2 of U in if U in is negative. So it's actually the definition of the absolute value function. So the output always will be positive. Yeah. For this circuit to work, what is important for this circuit to work properly? We need to have a very well tuned resistors, this one and this one, to have a ratio of 1/2, and to have this ratio of we have to have the load resistor equal to the sum of resistor R1 and R2. So if the load resistance will be changed because we attached, for instance, the next stage for the circuitry, so our rectifier wouldn't work correctly because this coefficient may be a little bit different. So it's important to keep the load resistor with no any change. So for this, to get this load resistor to be equal, always equal to this 3 kilo ohms, the next stage of our rectifier may be just a follower. We may use a follower as the next stage, yeah, to prevent the next stage, the next signal user, signal user to change, to load the resistor RL, to load our circuit and to change the resistance of this load resistor. Yeah? So the next stage usually should be follower. Some comment why I actually throw out the diode, yeah? Because the diode which is switched on in the circuit, it's actually need a forward bias voltage, but because of the operational amplifier, the voltage here in this point, the voltage here, it's automatically adjusted. What does it mean automatically adjusted? So actually this circuit because of the feedback, it's try to work to keep this voltage equal to 0, as we know. So when we have a negative voltage here, so it should be equal to 0. So if we consider the forward voltage, so that means that actually in the beginning, when the system sets up after the power is switched on, this forward voltage will be subtracted from the total voltage between input and output. And that means that for the first moment, this voltage may be a little bit lower than 0, because some of the voltage, or a little bit high, yes, a little bit lower than 0, because some of the voltage drops over the diode. But as the operational amplifier try to work to keep this voltage equal to 0, it's automatically rise a little bit the output voltage comparing to the simple inversion amplifier, which doesn't have a diode here. It's automatically increase this output voltage by diode forward bias to compensate this drop and to keep this voltage here equal to 0. Yeah. So it happens automatically. Speaking about diodes, probably a little bit going forward. So there is such a circuit for the diode, plus and minus, and I have here the diode included. So this circuit, so actually what it is, it's a follower. It's actually the follower when diode is included in a feedback. So when we apply here some positive voltage U in, so we will get for the first time, if it doesn't consider the diode, we have to have here the U in 2, yeah. But then the voltage here in this point will be equal U in minus U diode, forward diode. And it means that voltage here will be lower, the input voltage. The amplifier try to equalize these voltages. That's why in this point it's rise up his output voltage up to U in plus U diode. And due to this, voltage here will be just U in minus U diode plus U diode. And as a result, we get here just U in. So this is a circuit, just remember it, it's a follower when the diode is included in the output of the to the output of the amplifier. But the feedback include both the diode and the amplifier together. And this is a circuit which is known as an ideal diode. So this circuit doesn't have this drawback of diode of the forward bias. If we look how this circuit works, so if we look how this circuit works, it really works like that. So here we have nearly absolutely linear characteristic when we have U in and U out. Yeah? So the output will be absolutely equal to U in for the positive voltages, and we have nearly 0. Generally, it will not be 0. It will be some very, very small voltage related to the reversal current. But actually, it will be nearly 0 when the U in is lower than 0. So it's Yes, there will be the voltage which will be in the order of some microvolts, probably, or of probably some part of millivolt, yeah, which appears because of the flow, reversal flow of the diode, yeah, the leakage current of the diode. But it's a very useful circuit. So, and use of the amplifier together with the diode allow us to remove this dependence or this drawback of the forward current. So here's another example of the rectifier. It's a little bit more complicated. Actually discussing how this amplifier works, so we consider two cases, one more. So when we consider the positive voltage here, so when we consider that the positive voltage is applied, so we have positive voltage here, and then it means that the diode D2 is biased forward, and diode D1 is biased in reverse, so it actually doesn't allow current to flow through. So the current has to go through D2, then through this resistor R, and through the diode D3, making here the feedback. And the diode D4, in this case, is actually reverse biased too. So actually current go like that. It could go there, here, it go here, and then this second. So in this case, the first amplifier is working as non-inverting amplifier, which feedback is provided by these resistors, feedback resistor 1 minus XR and XR, and input resistor XR, and corresponding amplification will be just X, or 1 divided by X. So if I has yes, so this is if I have a negative voltage on the input, so then I get the diode D3 is biased, diode D4 is open, and I guess I will have the first, yes, diode D2 will be closed too, and D1 will be forward biased, and in this circuit the first amplifier will work now as a follower because of the feedback with the diode D1, which is open now, and the second amplifier is working as an inverting amplifier with the input voltage, input resistance, I guess correctly. So the input resistor, the D2 is closed. Yes, with the input resistor XR, so it's go like that. The negative, the voltage here is equal to voltage here, which is applied to resistor XR, part of the potentiometer, and the feedback R. Yeah, because the D3 is closed and the feedback provided through this way. Okay, and it works like inverting amplifier, and we have the same minus U input divided by X. So here we may not only rectify the signal, but amplify it too with a gain 1 divided by X. This depends on the position of this potentiometer. So of course we couldn't take X equal to 0 just because our output goes to the saturation. But generally this circuit combine rectification and amplification. So for you, please just consider at home these two conditions. So make a look on the first case when the positive voltage is applied, and then the diodes D2 and D3 are open, D1 and D4 closed, and here just D2 and D3 replaced just by lines, and D1 and D4 just removed. Yes, they are just removed from the circuit, and here we see indeed that the first is a non-inverting amplifier, and the second is a follower, and this follower just provides us here for here a virtual ground for non-inverting amplifier. Yeah. And the second example, yes, is The second example is when D1, D4 is open and D2, D3 closed. And indeed, the first is a follower, and the second now is just an inverting amplifier. So please review it one more at home, these both cases, trying to understand how the circuit works. Another example, next example what we are going to consider, it's so-called logarithmic amplifier. This is logarithmic amplifier or log amplifier use the feature of bipolar transistor or a diode. No, generally I take a bipolar transistor here. If we're trying to relate the collector current and the voltage over the base and emitter voltage over the transistor, we may find that the current through the transistor, the collector current, is related to the base emitter voltage following this equation. So this is a coefficient which actually depends on the transistor itself, and IS, it's actually the current. It's a collector. It's a current of the closed collector. So it's actually the leakage current through the collector. It's very small. Here, for example, for this example, it's taken 10 minus 13 amperes. But generally, we see that the relationship between base emitter voltage of the transistor and the collector current is logarithmic. So let's consider such a circuit. Let's consider such a circuit. So we actually apply voltage U1, UE input. Input voltage causes a current through resistor R1 to the 0. So the currents go here because this is this is actually virtual zero because we have a feedback. Now we understand whether we really have a feedback. So let's consider we have some kind of positive voltage. So and the positive voltage for positive current will be applied to this inverting input. It means that output should be negative. So if output is negative, it's minus. It cause an emitter current or base emitter current flows through the transistor. So the transistor will be open. The transistor will be open, and the current which flow through the resistor Ri will flow through the transistor collector too. So the transistor is open, and then we have the current that flow through the collector. The output voltage will be exactly the voltage between base and emitter, and we know that it's a logarithm of the collector current. The collector current itself is a current through the input resistor. So combining it together, actually the E collector is equal to U1 UE divided by Ri, and we have to put it here, and we will get that the output voltage, which is equal to base emitter voltage, is equal to the logarithm of the input current. This is proportional, the logarithm of the input current. What is important? What is important that the input current, the output current will be negative. So the output voltage actually equal to the minus base emitter voltage because it's negative here. Well, and we see that in this side, in this side. So for the positive input voltages, the output voltage will be more or less, not very accurately, but generally it will be proportional to the logarithm of the input current. We may add some outer circuitry. For example, here we add a circuitry with some kind of feedback resistor and 1/9 of the feedback resistor. And for this case, for such a, if I connect this base emitter current not directly to the output but through the feedback resistor, it could be demonstrated that the output will be equal to the logarithm of this, proportional to this, the same logarithm as with a logarithm of the current as without these feedback resistors, but multiplied by 10. So I may add here some scaling circuit which allow me to scale my logarithm. So I may change it a little bit. This is a logarithmic amplifier. So make sure that they are inverting amplifiers. So if you're going to use the positive voltage, we have to invert the output, but nevertheless it works pretty well. Well, if I use a logarithm, a transistor in a feedback circuit to get a log amplifier, which calculate me some signal which our output is proportional to the logarithm of the input, how should we design an anti-log amplifier? So that when the output will be proportional to the anti-log of the input, or input will be log of the output. So if here we have a transistor on a feedback, where should I put a transistor in anti-log amplifier? Is there any ideas? So look at this. So we have this relationship. Yeah, U is proportional to the log of I. So I put here transistor. So my output voltage is proportional to the logarithm of input current. Now I wish to get the anti-log. So I may write that my current is proportional to the anti-log from U. So I have to get some here in the output, some current that is proportional to the anti-log of the voltage. So where I have to include my transistor? Any ideas?
The base goes to the output.
No. Actually, I have to put it on the input. So here it's in the feedback, and I will put it in the input, like that. So I may take a diode, and here I use the fact that the current through the diode is somehow proportional to the exponential of the voltage over the diode. It's a well-known formula. Or I use my transistor, and for the transistor, one more. Let's see that if the voltage over the base, between base and emitter, is proportional to the log of EC. So let's write down. So I couldn't mark it as do it as a pointer itself. So if I have actually from this equation, why? So from this equation, actually, very roughly speaking, U by E is proportional to the log of IC. The proportionality coefficient is not so important. So all these parts, they are related to the proportionality. Yeah? So it means that IC is proportional to the 10 in the power of UBE. And look at this now. Look at this now. I apply voltage V1, which is actually the voltage between base and emitter for this transistor. And this causes the collector current IC. And this collector current IC will be proportional to the 10 in the power of U base emitter, which in my case is 10 in the power of V input. And then the output voltage, V output, will be just the feedback resistance multiplied by this current. It will be proportional to the 10 in the power of V in. Of course, the proportionality coefficient plays some role. Here, with the diode, we actually use the same. We use the current through the diode, the direct current through the diode is approximately proportional to the exponent in the power of voltage times some coefficient. Not matter what this coefficient is, but generally the current through the diode proportional to the exponential of the voltage. It means that the output current, V output voltage, which is RF times current this flow through the diode will be proportional to E in the power of V times some coefficient B. So I will get the anti-logarithmic amplifier. So, and having both logarithmic and anti-logarithmic amplifier, I may try to make the circuit which is named a multiplier. Quite one of the important circuit, very important circuit in the data processing and signal processing. It's a multiplier. So the circuit that may multiply two different signals. There is different way how to assemble such a circuit, and one of the most straightforward ways is to use the known relationship between the product and logarithm of the product. So actually, if we have so we need here, we use here a very well-known mathematical notation. So the logarithm, I use the decimal, for example, the logarithm of the product is equal to the sum of the logarithm. So this means that we may take a log amplifiers, we may take a log amplifier. To make a logarithmic, get the logarithms of the both signals, add them together, and then we have to use the antilog. And then we have to use the antilog to put back this, to take the opposite, yes, to get to come back from the logarithm of the product to the product itself. So that's why the analog multiplier, one of the designs of the analog multiplier, it's antilog. It's a log, summation, and then antilog. Speaking about multiplier, we need immediately discuss. We need to discuss. So we still have some time. Yeah, we have to discuss such a concept. So the multipliers are divided or are actually grouped by the range of the signal they may work with. So if we take the voltage U1 and U2, so the simplest one, for example, if I take this one without any additional transformation, just like we discussed, the log amplifier, summation amplifier, anti-log amplifier. As you see, the log amplifier actually, this one, may operate only at the positive voltages. So if input voltage is positive, we will get this logarithm. If the voltage is negative, so we have plus on the output, and this plus of the output actually block base, and it's actually block the transistor current, the collector current at all, because the base, the emitter base junction will be reverse biased and transistor will be closed. So the output voltage is just maximal positive. So it means that there is no, if the current, the collector current for the transistor is blocked here, we have actually the feedback destroyed. There is no feedback anymore, and the amplifier will go to the saturation, just show maximal positive voltage. Yeah? And so for this log amplifier, the input voltages may be only positive. And if both of the input voltages are positive, we have so-called one quadrant multiplier. So it works only in the first quadrant, so only here. So we may work only with both positive voltages. Some of the analog multiplier use a little bit another principle. For instance, it may be inverting or non-inverting amplifier when a feedback resistor is actually an electronically controlled switch or an electronically controlled resistance, like a field transistor, for instance. Yeah? And then one of the input voltages is an amplifier input voltage, and it can be both negative and positive for the inverting amplifier. But the second voltage, which control the feedback resistor, may be only positive. For the field transistor to operate correctly, it should be unipolar. It will be unipolar, and we get so-called two-quadrant amplifier. So the two-quadrant amplifier works with one of the input voltages. One of the input voltages is both maybe both positive and negative, U1 for example, but U2 may be only positive. And finally, the most all-purpose and the most, let's say, advanced is a 4-quadrant multiplier, which could be used in any of these 4 quadrants. So, and the signals may be both positives and negatives. Well, some comments how to get such type of multiplier. So generally the circuit what is depicted here, which is thought to work with only positive voltages U1 and U2, looks like this. So indeed, we have a positive voltages V1 and V2. We have two logarithmic amplifier when use not a transistor but a diodes. And they rely on this relationship between the diode current and diode voltage. So the opposite, so actually the current through the diode is related to the voltage through the diode via this relationship. So we have some kind of addition here, some additive component, yes, which little bit deforms the operation of our amplifiers. But nevertheless, these two amplifiers with the diode in a feedback, yes, they both work as logarithmic amplifiers. As a resulting logarithmic signals are added together using this summation amplifier. As both logarithmic amplifier are inverting and the summation amplifier is inverting too, then when the signal is positive here, it becomes negative after logarithm operation, and one more becomes positive after summing. So here we have a positive voltage, and here we have anti-log amplifier with the diode and the input. The result, if we look at the result, so when two signal V1 and V2 voltages in V2 applied to this circuit, it may be demonstrated that the voltage here, actually after, it's rather say here, after the anti-log amplifier, actually this voltage VB is related to the voltage on the input here on the input of the diode, or sorry, of the voltage. Yes, actually voltage applied to the diode, and if it will be, if we calculate it correctly, we see that generally this output voltage VB will be equal to the multiplication of V1 times V2, this product of these two voltages, divided by some constant. Generally, this constant is related to the resistance R, what is used all over the circuit, and the dark current of the diodes here. So IS, it's a dark current of the diodes. If so, but it's not will not be an accurately V1 times V2. It will be V1 times V2 times this coefficient minus V1 plus V2, because both logarithmic circuit and anti-logarithmic circuit has here this addition 1. And it may be demonstrated that the output voltage here will be like this. The product with some coefficient minus V1 plus V2. That's why the final stage of this multiplier is another summing amplifier, which actually add V1 and V2, the same as here, it's just they are going in parallel, both in the input of the log amplifiers and in the summing amplifier. So they will actually add V1 and V2, and we get V out accurately only minus V1 V2 divided by RIS. So generally we get what we want. If you want, we may scale the output, yes, by this number, by selecting some relationship, changing a little bit this resistance. So we may actually scale it, or we may apply the next inverting amplifier, which scale as the voltage and turn it around to the positive V1 times V2, and immediately and simultaneously scale it to provide us just output voltage equal to the product of the input voltage. So this is but what is important that this is one quadrant multiplier. So it may work with the V1 positive and V2 positive. It couldn't work with the negative V1 and V2. To work with, I just make some note here upstairs. To work with a non-positive V1 and V2, what could we do? So if we're going to multiply V1, which is in the range of minus V0 up to V0, so we want to work with the voltages in this range, both V1 and V2. What we actually could do, we actually may come from V1, may add using before we send the data to the multiplier, we may to transfer our V1 by adding a V0. And then the result will be changed from 0 to double V0, but will be positive. The same we will do with the second voltage. We transfer it to the voltage V2 plus V0. It will be in this range too. Then let's see what happens if we multiply these two voltages, already transformed voltages, using these multipliers. So we get actually what we actually get. We get V1 plus V0 times V2 plus V0, which give us product V1 V2 plus V1 V0 plus V2 V0 plus V0 square. So what actually should we do? So V0, as we control V0 by our own, we select this V0, so we know exactly what the V0 square is, and we rewrite it like that. So it's V1 V2 plus V0 times V1 V2, V1 plus V2, and plus V0 2. So actually, what should we do? We should use as first some summating amplifier to increase both V1 and V2 by V0. Then we multiply them both, and then we send an output to the other summing amplifier. When we subtract V1 and V2, scale it to be multiplied by V0, and we extract some constant voltage which is numerically should be equal to V0 squared. So we may actually adding a two others before and one other with 4 inputs after. So we will get the 4-quadrant multiplier. And this is the example of operation for this chip AD835. It's an example of the 4-quadrant multiplier. And even more, it works it has the two differential inputs. Actually, it's calculate on the output the product between difference x2 minus x1, or x1 minus x2 and y1 minus y2. So it calculates the product. And then actually, and if you find the data sheet of this amplifier, you will find that the range of these differences, x1 minus x2, is pretty small. The range of x1 minus of input or either x or y, so x1 minus x2 should be less, by absolute value, should be less to 1.2 volts. So it's very small. If it fed with a 5 volts, because actually these differences are shifted to be calculated, the difference to be shifted to be measured in respect to the V0 equal to 2.5 volts, and then we have only approximately 1 volt up and 1 volt down, 1 volt up and 1 volt down before the saturation of the circuitries, and then they could be multiplied. So for this, and we have to provide that the product will not saturate. The product will not saturate. So that's why the input range of this actually these numbers that we are going to multiply, they are not so high. So you will find it. But nevertheless, we always made to scale signals before we send them to the multiplier, and then scale them back after the product is obtained. Okay, we will stop up to now because only time is finished. So we meet next Tuesday as usually. So please ignore this task one more. So I reassigned the task for the next class. So where it was. don't see my orthos. There are too many. Ah, here is it. Yeah. So please don't yet look at this. Don't please yet look at this task homework assignment. Yeah. I will change the schedule and it will be due for the next, not for the next class, but after the next class. So I will make inactive only next class. Yeah. So we consider how to calculate this circuitry. Yeah. Okay. So let's stop for today. And thank you for attention and see you next Tuesday. Bye bye.